Across a white horizon, new bases, buried utilities, and hard-won corridors are stitched into ice and rock to keep people, cargo, and signals moving. The make-or-break constraint is anchoring precision in ground that moves and melts. Crews turn to pile drivers, rodomes, heated pipelines, and icebreakers. Machines built to cut, lift, seal, and hold position in brutal conditions. Miss an alignment or a curing window and the whole schedule ripples. In minutes, we'll reveal the sequence, the single trick that lets them lock towers to permafrost, enclose radar and fabric, and carve lanes through moving ice. The mission is to move people, goods, power, and data across a frozen ocean and a thaw-prone coastline, while keeping watch over the sky and sea. The stakes are clear. If coverage drops, blind spots open during storms. The network must provide near-instant handoff to keep watch continuous. If power blinks in the long dark, everything from heat tracing to communications risks cascade failure. If sea access closes, cargo strands and projects stall, so ice-capable hulls and seasonal planning keep a narrow window alive most years. To ensure any of this works, they first have to measure a ground that refuses to behave. Before they can build, they must know exactly what they're building on: ice, silt, rock, and moving water. Permafrost can look solid and still slump if warmed. Crews sink test bores and install instrument strings, taking regular thermistor logs and repeat survey pins to map strength and thaw risk across seasons. Where utilities must cross freeze-thaw zones, cables and pipelines are trenched into stable strata. Deep trenches reduce heave, abrasion, and unintended warming. Road and airfield approaches start with geotextile and graded fill to spread load and isolate warmth from the ground, so the surface rides out winter cold and spring softening. Read the layers wrong and every foundation, seal, and runway alignment becomes a rework domino. With conditions mapped, the build becomes a system of subsystems that must share power, tolerate cold, and align within tight tolerances. Load gets transferred through piles, mats, and towers, while designs keep the ground cold. Envelopes of fabric domes and insulated skins shed wind and ice, creating stable microclimates for equipment. Buried power, heated pipelines, and ventilated enclosures keep fluids moving and systems within safe operating ranges. Radar, beacons, and sensors tie into redundant data backbones to provide awareness and command. Stabilized roads, all-weather airfields, and marine touchpoints fed by ice-capable vessels and pontoons keep logistics flowing. The critical interface is where hot surfaces cross cold joints. Get electric heat trace and insulation wrong, and you freeze, split, or leak. Joints where hot meets cold are single-point failures and demand the most attention. To put steel and equipment on this ground, crews first create access that won't sink. They can't pour concrete or place towers until roads, staging, and marine touchpoints exist. Crews roll geotextile over prepared subgrade, then add graded aggregate to spread pressure and slow heat transfer into permafrost. Floating pontoons and, where conditions and permits allow, layered ice pads create temporary berths to offload vessels and position cranes. Tracked carriers shuttle oversized drill rigs and modules without punching through crusted snow, and ice-capable ships push materials in during narrow weather windows. Staging camps and modular units arrive early so more crews can work in parallel. Insulated accommodation and plant modules compress on-site assembly, scaling from dozens to hundreds depending on the project. With access secured, the next problem is getting loads into the ground without waking the permafrost beneath. Heat is the enemy. If the subsurface warms, bearing capacity drops and structures settle. Foundations use ground cooling piles that draw heat away so the supporting soil stays frozen through summer peaks. Some systems rely on passive conduction loops, others on active chilling. Where towers face severe gusts, cores extend down to competent strata, often tens of meters, using drilling methods that keep frozen boreholes open long enough to place casings and backfill. When concrete is unavoidable, cold weather mixes and tightly tied reinforcing cages are scheduled into brief, warm windows and protected to avoid thermal shock. Bridges and elevated decks are proven with load tests that check combined effects of temperature, vehicle load, and differential settlement. Mitigation always pairs ground cooling with temperature monitoring, so crews can respond before thaw-driven settlement threatens utilities. Once anchored, the project repeats thousands of precise moves, and tempo and accuracy must hold before the weather turns. The job becomes a steady cycle. Surveyors cut through snow to reveal benchmarks, drive pins, and mark lines and elevations. They seed control points across pads, roads, and towers, so every component lands true despite drifting snow and low visibility. Teams pre-build modules in controlled shelters so welds, seals, and coatings cure correctly before facing the cold. Pipe spools, skids, and tower sections arrive tagged and tested, ready for quick hookup. Cranes set structural pieces on prepared saddles, pours lock rebar into mats, and pile caps under heated blankets. And crews drop in utilities while runway lights and navigation aids are set, sealed, and aligned for low visibility operations. Pipelines get electric heat tracing with insulated runs to keep fluids above freezing. Long conveyor stretches use cold-resistant belt compounds and low-temperature bearings. Electrical and data backbones are pulled through insulated trays and glands that won't crack in deep cold. Every placement is checked for alignment, insulation continuity, torque, and seal integrity. Punch lists close only when test sheets and tags match the plan. Prefabrication and tracked movers let parallel crews advance on multiple fronts. When winds scrub a lift, teams pivot under cover to fit out modules, pull cable, or test subsystems so the cycle never fully stops. Then comes the centerpiece, the moment that looks impossible from shore. Set the array, seal it under a dome, and bring it to life. A radar face, tens of tons, rises on synchronized cranes guided by taglines and live wind monitors. Crews ease it onto machined bearings and seat it square. Connections are torqued in sequence to avoid distortion. Alignment targets confirm the axis before anything is enclosed. Power, data, and de-icing services route through flexible, insulated runs with proper strain relief while alignment sensors verify the array points true. A reinforced fabric shell unfurls and inflates, creating a pressurized, dry microclimate that sheds wind and icing. In calm conditions, the dome stabilizes within hours. Technicians step through hold points, alignment checks, seam integrity and pressure tests, and functional sweeps before handing the array over to the redundant backbone. If winds or seam thresholds are exceeded, the plan pauses, reduce inflation, secure edges, protect bearings, and return to alignment without overstressing the fabric. To keep materials flowing, a marine and over-ice logistics machine spins up. Bulk and oversized components ride in on ice-capable convoys timed to short weather windows. Where harbors don't exist, floating pontoons form temporary berths for offload and staging. Undersea cables are buried beneath the seabed to protect data links from scouring ice keels. Autonomous vehicles and drifting sensors reconnoiter routes and update seabed and ice maps regularly after melt events. Dynamic positioning holds ships on station between flows so cranes can work without anchors. Dredging and drag reduction systems appear only where viable and permitted, carving deeper lanes and easing hull-ice interaction during critical deliveries. A build this exposed lives or dies on verification. Liners get seam-by-seam heat weld checks with vacuum or spark tests where appropriate. Pressure and leak tests prove pipelines and heat trace integrity before fluids ever flow. Welds on cold exposed steel follow qualified procedures and consumables for low temperatures, then undergo non-destructive testing for cracks and inclusions. Load and alignment tests validate bridges, rotating equipment, and towers. Lab checks on drill cores and samples at regular intervals, informed by the geotechnical program, confirm ground or ore properties before full commitment. Perimeter sensors ring critical containment to detect seepage early. Acceptance criteria are defined by permit and test protocol, and every batch, weld, and test is tagged and signed off, building a traceable record from fabrication to commissioning. With gear finally on site, all the pieces have to talk and back each other up. A buried plant and a seasonal hybrid mix feed a hardened microgrid that powers heat tracing, ventilation, and communications without relying on a single source. Seasonal renewables can offset summer loads where feasible, while reserve generators stand ready to carry critical services during prolonged storms. Deep trenched cables and insulated enclosures guard data and control lines. Radar and beacons fold into a redundant network for awareness in low light and fog. Redundancy is made practical with isolation valves, bypass feeders, and tested failover drills so a tripped heater or a dropped feeder doesn't take the system down. Integration is iterative. Energize, tune, run failovers, repair weak links, and repeat until the machine behaves the same in calm and in a whiteout. Then it is time for first flow, first lift, and first data. Commissioning climbs a ladder. Inflate and hold pressure on enclosures, perform functional sweeps on arrays and communications, and then tie into live networks. Marine access proves out with an escorted convoy, dynamic positioned offload, and communications checks while cranes work between flows. Processing pilots run in the cold to confirm chemistry and separation in field conditions, while containment and water treatment close loops aimed at high reuse where feasible. Structural elements are rechecked under service conditions to validate models before opening to routine traffic. Even after the firsts, maintenance access, seasonal procedures, and upgrade paths lock in a life cycle plan that matches the climate. If this sequence holds, the site moves from fragile to operable. First flow, first lift, first data.